In this video, we're going to do some guided exam question practice on a 2017 question that came up on electron arrangement and first ionization energies. So it's a full question, so it's a 50 marker. It gives you about 20 minutes to do it in the exam. So get your timer and let's get started. All right, so let's jump into it. First question, define atomic orbital. So that's the first thing I ask you to do, straight into a definition where you have to define. Okay, so that's what it means, define, and that just means explain what an atomic orbital is. Okay, so I'm going to go ahead, jump over here, write down what the definition for atomic orbital is. Pause the video and do that now. Okay, so this is part A. What is the definition for atomic orbital? Okay, this is what you should have said. Again, I'm not going to waste my time writing it down. You need to know this word perfect, and you should definitely recognize this, and I've written it down loads and loads of times. So the definition for atomic orbital is as follows. It's the region in space where there's a high probability of finding an electron, or it's a region in space around a nucleus where there's a high probability of finding an electron. Second one is probably slightly more accurate. Okay, so that's what we want. That's what we want there. Let's look at the next bit. It says write. So it wants us to write the ground state, so unexcited sp configuration of a carbon atom. All right, so that's the second bit. So notice the way they're not actually numbered here separately. It would be nice if they did this, and then it would be easy for us to not forget any of these, but they haven't done that, which means we have to be really careful that we don't just define atomic orbital and then forget to go back to it and go to part B, because then we're in trouble because we're missing all of this here. We're going to be really careful here. So write the ground state sp configuration for a carbon atom. All right, so carbon atom. Okay, so pause the video, write that down now. Okay, so if you haven't done this already, the first thing you're going to need to work out is get your periodic table, work out how many electrons a carbon atom has. So if you haven't done that, you didn't know how to get started, pause the video, do that now. Okay, carbon atoms have 6 electrons. The symbol is capital C, and you need to write the electronic configuration, the sp configuration. So now I've told you 6 electrons, you might be able to pause the video and do that now. All right, so if you haven't started and you had no idea how to begin, I would begin by writing down 1s2. So now that you see what I'm doing, maybe you can finish it if you couldn't already do that. Pause the video and do it now. Okay, so 1s2, 2s2, 2p2. That's pretty much it, guys. Okay, there's 6 electrons altogether. So it's going to be 1s2, 2s2, 2p2. That's it. That's all there is. Only 6 electrons. Okay, so the next question is, okay, this is where we need to be careful. How many orbitals are occupied? Okay, how many orbitals are occupied? Now be really careful. People will just see this and go, oh, there's 3 things, so it's 3 orbitals. It's not 3. Okay, so if you think you know how to do this, pause the video and work out how many orbitals have electrons in them. Do that now. Okay, if you didn't know this, if you didn't know how to do this, I'm going to give you a clue as to how you would do it. I want you to draw an electron spin diagram for this, and that will tell you how many orbitals have electrons in it. Do that now, please. Okay, so hopefully you did an electron spin diagram like this. This is the 1s sublevel. This is the 2s sublevel, and this is the 2p sublevel with 3 orbitals in it. 2p. Okay, so if you didn't know what I was talking about when I said to draw a spin diagram, this is it. Do this now, put the electrons in here. Okay, so hopefully you've drawn in the electrons. Okay, and if you've done that, you should be able to write down how many orbitals are occupied. So underneath here, I want you to write down a certain number. Orbitals are occupied. Write a sentence like that at the end. Okay, so pause the video and make sure you do that now. All right, this is what we should have done. For the 1s, there are 2 electrons per orbital. So there are 2 electrons here. This is the 1s2, shows us 2 here. There are 2 electrons here. This is 1 spin up and 1 spin down. And there are 2 electrons in the 2p. But there's a rule for how we fill these, and that is that electrons will occupy orbitals singly before occupying them in pairs, where there is more than 1 orbital of equal energy. So these are 3 orbitals of equal energy. That means the electrons will occupy these orbitals singly before occupying them in pairs. So there's the 2 electrons. They go 1 into each. Now, if we count them up, you can see that's an orbital, that's an orbital, that's an orbital, and that's an orbital. So 4 orbitals are occupied, not 3. Okay. So again, if you do the spin diagram, that made it much easier for you to know. So if you're ever asked how many orbitals are occupied, spin diagram. Okay, let's go and look at the next one. Why is it difficult to specify the absolute boundary of an atom? Why is it difficult to specify where the edge is, in other words, the absolute boundary of an atom? Okay, so again, we have seen this question before. So we're writing, this is part B, and we're writing about boundaries of atoms. Why is it very hard to say where the boundary is? Pause the video and write down what is it that makes it hard for us to tell where the edge of the atom is. Okay, so what they're really looking for here, well, it's got to do with Heisenberg's uncertainty principle, okay, because that doesn't let us know where the edge of the atom is, because we don't know the absolute limit of where the electron can go. Okay, so we can't, it's very hard to know with any certainty the position of the electron. So we can't say, oh, it's definitely always inside this boundary. Okay, so it's due to the Heisenberg uncertainty principle. Heisenberg uncertainty principle. And hopefully you wrote that down. You mentioned the uncertainty principle in your answer. Okay, so that answers the question. Why is it difficult to specify the absolute boundary of an atom? Well, it's because of the Heisenberg uncertainty principle says you can't know the exact position of the electron and the exact velocity at the same time. So you could have also written down what Heisenberg's uncertainty principle says. We'll see the Martin scheme later. Next one, state the definition used for the covalent or the atomic radius of an atom. Okay, so atomic radius, covalent radius, same thing. So we're asked for a definition, atomic radius. Pause the video and write down the definition for the atomic radius of an atom. Do that now. Okay, so if you weren't sure about this, guys, if you don't remember this, I'm going to draw a diagram that might help you to remember. We've got a covalent bond between 2 atoms. So here are 2 atoms. They are covalently bonded. They are the exact same atom. They are the same size. And we would find the radius by looking at this distance and taking that distance, d, and doing d divided by 2. So that might help you, that diagram might help you to think about d or half d. D divided by 2 or half of d, same thing. That might help you to think about the definition over here and write it down. Okay, this is what you should have written. I'm only going to read it out for you. You guys can pause it and listen to me if you need to. It's half the distance between the nuclei of 2 identical covalently bonded atoms. That's the atomic or covalent radius. This is how we find out how far is it from between 2 atoms, between the nuclei of 2 atoms. So take a line between them here, divide it in 2. And that should be the edge of one of the atoms and the edge of the other of the atoms. And because they're both the same atom, well, it's the edge of either of the atoms. That's the atomic radius. Okay, it's not possible to just take a line from the nucleus to the edge of the atom and measure that because we don't know where the edge of the electron is. What we do know is how far apart 2 nuclei are, and we can measure that distance divided by 2, and that should be the edge of one of the atoms. Okay, so that's the atomic radius. Next bit. Okay, so on to part C now. Okay, so let's see what it says here. This is, it says describe and account for the general trend in covalent radius down group 1 of the periodic table. So describe and account for, that means describe and give reasons. So what we're going to do is we are going to let's line this out. We're going to say C, we're going to describe is part 1. And then in part 2, account. Okay, so it's the general trend in the atomic radius down group 1. Pause video and describe. Okay, so this is what you should have said. You should only be listening if you describe the trend down group 1 of the atomic radius. You should have said what happens to the radius. Radius increases down group 1. Down group 1. Okay, that's what happens. Atoms get bigger. Account for, pause the video and account for. What happens as you move down that makes it get bigger? Okay, so, well, you're adding a new energy level or shell. New energy levels are added. That's what we're doing. We're filling up more electrons into more shells, and that makes the radius get bigger. So as you move down, radius gets bigger. You also have the whole thing of, well, there's more screening, which lets that further electron go further and further away because there's more inner shells, which means that you've got less pull of the nuclear charge. So atomic radius is getting bigger because you're adding more shells and there's more screening. But definitely this is the important one, new shells being added. Right, let's go back. That was 9 marks, was it? No, that was only for the first part. It says then the bar chart, so it's referring to something. It says the bar chart, so this must be it down here. What does it show? It shows the covalent or the atomic radius for the atoms of the elements of the second period. So we're going across a period of the periodic table and it excludes neon. So we don't have neon. Account for the general trend shown. Okay, so there's the question. Account, don't miss that. Okay, notice that we could easily miss that and look down below the graph. Oh, there's no question, I'll keep going. Be careful. Here's the question. Account for the general trend shown. So before I go any further, I'm going to go part 2, account, just so I can't forget to do that. So that's why it's really important to lay out your question like this. All right, so let's look at the graph again. I've got element number 3. This is in the second period. This is lithium. And then I've got element number 9. So this is in period 2 again. And it's excluding neon. So it's the one before neon. Look at your periodic table if you have to. I know that that's fluorine. So lithium to fluorine. And we're being asked to account for the general trend shown. Now, to be honest with you, this here is all fluffy information because I already know from class what happens to atomic radius. But I can, if I forgot what happens to atomic radius, I can look here. The radius, what's happening? It's getting smaller. Okay, so this shows a general decrease. What? It shows it's going down essentially. Okay, so what exactly is happening? Account for the general trend shown. So talk about what's happening. Well, what happens to the radius and why? Let's write that down now. Okay, so hopefully it said that the radius is decreasing. Oh, so the radius decreases, which is obvious from the graph. Due to what causes that? What are the things that cause it? All right. So thinking about what happens as you go across group 2 that would make the atoms get smaller and smaller and smaller. Okay, well, there are a couple of things happening. The first one is that the nuclear charge, what's happening to it? What's happening to the nuclear charge? Okay, so finish that off. The nuclear charge does what? And the second thing is the screening effect. What happens to it as we go across? Okay, so pause the video and finish those sentences for me. Radius decreases due to, okay, so hopefully you've had a go at these. Well, what's happening to nuclear charge? Due to nuclear charge is increasing. We are adding more protons, so the nuclear charge is increasing. And the screening effect, what happens to it? Well, all the electrons are getting added to the same shell as we go across, which means that there's no increase there, no change to a screening. So the screening effect does not change. Okay. Another way of saying these two things together, and this is what you did instead, if you did it by yourself, is that you might have said that the effective nuclear charge decreases. No, increases, sorry. So the effective nuclear charge increases. If you said that by yourself, then that's perfectly fine. Some of my class will know what that means, effective nuclear charge. Effective nuclear charge puts these two things together. That's why we only need to say this one line if we do say it. But if we don't, then we need to say these two lines together. So the effective nuclear charge essentially takes the nuclear charge that's increasing and takes away the screening effect from it. Well, if the nuclear charge is getting bigger and bigger and bigger, and the screening effect is remaining the same, well, then overall how effective the nuclear charge is getting more and more effective. So because that's getting more effective, it's basically pulling in the outer electrons and making the atoms smaller. All right, guys, that's that one. Okay, so let's have a look then at part D. So again, we've got another definition. So it says define the first ionization energy of an isolated atom in its ground state. Okay, so what I need you guys to do is I need you guys to go ahead and do that definition. So this is part D, and this is the definition for first ionization energy. Pause the video and write that down. You guys should know that by now. Okay, so this is what you should have done, guys. It's the minimum energy required. So again, I'm going to speak this. You can pause it, rewind it, listen to me saying it again if you need to. I'm not going to waste my time writing it down. It's the minimum energy required to remove the most loosely bound electron from an atom in its ground state, okay, or from a mole of atoms in the ground state. All right, so again, rewind that back and listen to me saying it if you need to check, or if you didn't get it and you need to write it down. Let's look at the next bit. It says why. Why? So explain why do first ionization energy values show a general increase across the second period of the periodic table. Okay, so again, it's getting a little bit complicated now, and I'll tell you why. The reason why it's getting a little bit complicated is because we're mixing up atomic radius and first ionization energy trends here, which can mean that you can get a little bit confused. So just be careful and be absolutely sure. So we're talking about explain why first ionization, sorry, I'm just going to say IE for ionization energy. First ionization energy, what happens to it? Let's just read the trend again. Why there is a general increase across the second period. So first ionization energy increase across period 2. So explain why that happens. Okay, so talk to me about some of the reasons why that happens. Okay, so again, thinking about what else is happening that's going to cause it to be harder to remove an electron. If the first ionization energy increases, it's getting harder to remove an electron. Pause the video, do that now. Okay, right, so here we go. Well, what's happening is, again, it's actually the similar reasons to above. What's happening is that the nuclear charge is increasing, so the atoms become more positive. Nuclear charge is increasing. Okay, nuclear charge is increasing. And what's happening to, what's happening to the size of the atom? What's happening to the size of the atom? So what's happened to the size of the atom? Pause the video and write that down. Okay, so the nuclear charge is increasing, and also the other factor here on first ionization energy is that the atomic radius is decreasing, which means the atom is smaller, making it harder to take away the electron from it because the outer electrons are closer to the positive nucleus. So the nucleus is more positive and the outer electron is closer to the nucleus, means that it's harder to remove that outer electron. Notice some people will go for screening here. The nuclear charge is increasing and the screening is like not changing, but the screening has no effect really on first ionization energy, as in like screening would actually make it, if there was more screening, it would make it easier to remove an electron. So we don't want to know, we want to know why is it harder to remove an electron as we go across. So one of the things is that it's getting more positive, harder to remove, and the atoms get smaller, which makes it harder to remove. All right, let's go and look again at the last little section here. Okay, so it says here, the full set of ionization energy values for the electrons in carbon. Okay, so we're talking about the electrons in carbon, and it's the full set, which means we're moving all of them one after another in kilojoules per mole, and in order, starting with the first is, so this is the first electron, this is the first ionization energy, and then presumably then it works its way up all the way to the sixth and last electron. Sixth and last. All right, so look at the difference between the first and the last one. All right, but definitely before I even look at any questions, I'm looking for a pattern. I'm seeing 1086, 23534. Okay, what I'm seeing is a definite increase. Definitely gets harder to remove an electron each successive ionization. All right, so how does this set of numbers provide evidence for? Okay, so how does this set of numbers provide evidence for the number of electrons in the carbon atom? How does it prove that how does this set of data prove that there are 6 electrons in carbon? Well, there's 6 results, okay? So it's saying the successive ionization for all of the electrons in carbon starting with the first, and then after the first, there's 6 values to remove the electrons. So how does it prove that there are 6 electrons or there's 6 values? So it's that simple, okay? So again, it could get complicated. We could make this very complicated in our heads, but it really is 6 values means there are 6 electrons. Okay, so it is that simple. Don't want to overcomplicate it. That's what it says. There's 6 values. There must be 6 electrons. Each one of them requires energy to remove. How does it prove the number of electrons in each main energy level in a carbon atom? Okay, how does it prove the number of electrons are in each main energy level in the carbon atom? If we think about a carbon atom for a second, here's the nucleus. Here are 2 electrons in the first energy level. How many electrons are there in the second then? Well, there's 6 altogether, which means there's 4 in the second energy level. So how do these numbers prove that there are how many electrons can be in each main energy level? Well, what do I see here? I see 1086, 235, 4. All of these are gradual increases. Do you see this? So going from 1,000 to 2,000 to 4,000 to 6,000, that's gradual. That's the first 4 electrons. And then the 4th electron, the 5th electron, look at that. Massive increase. Massive increase. And then the 6th electron to empty that one, well, that's actually a massive as well. So these are way, way, way bigger. So that massive jump between the 4th and 5th electron, that kind of proves how many electrons are in each of these shells. After the 4th one, to remove the 5th one, it's an extremely large jump. Okay, so what does this prove for us then? What can we say about this? All right, so pause the video, explain how, let's show you the question again, see if you guys can actually do this. Explain how the data set provides evidence for the number of electrons in each main energy level in a carbon atom. I'm going to give you a chance to pause the video and try that for yourself now, okay? So pause the video and do that now. Okay, this is what I would say here. This is, and again, this is like this is the little bit at the end that really separates the H1 from the H2. Okay, that this is a pattern that we might not have talked about in class, but they expect you to be able to look at that set of numbers and figure it out. Okay, so well, what would we say? We would say there was a gradual increase in energies for the first 4 electrons. That's what I would have said, which this shows there are 4 electrons in which energy level? Pause the video and include that if you haven't said it. There are 4 electrons in the second energy level. That's what it seems to show. What else do we notice then? There is a massive jump between the 4th and 5th value, showing the final 2 electrons come from the first energy level. That's what I would say, first energy level. Okay, I'm going to read my answer again, see does it make sense. There's a gradual increase in energies for the first 4 electrons. What does this show? This shows us that there are 4 electrons in the second energy level. Then there's a massive jump, which kind of shows us that, okay, well, something new is happening here. What is the new thing? Well, these must be coming from an energy level where it's harder to take electrons from. So this must be closer to the nucleus. So there's a massive jump between the 4th and 5th value, showing the final 2 electrons come from the first energy level. All right, at this stage, I've shown you how to correct your answers using the marking scheme. So what I'm going to do is I'm not really going to talk you through it at this stage. I'm just going to put it up here for you. You guys know how to use this now. So I'm going to ask you, I've got A and B on the screen now. So I'm going to get you to pause that, okay, and go ahead and correct your answers. They should be pretty okay if they match my ones. Okay, and now that you've done that, here's part C, D, and E. So you couldn't see it all in one go. So now there's C, D, and E. Pause and go correct those bits. And that's it. That's a full question, guys. That was a toughy question, I suppose, with lots of trends and stuff there. But if you know your stuff here, it's not too bad. That's that one. And I'll see you in the next video.